In the previous several lectures, we discussed the concept known as mutual inductance. Now, let's examine a similar concept known as self-inductance or simply inductance. So let's begin by looking at the following diagram. Let's suppose we have a coil of wire. So this coil consists of some number of loops. Now, what will happen inside our coil of wire when we allow an alternating electric current to flow through this wire as shown by the following orange arrows? Now, when our electric current travels through the loops of wire, it will create a magnetic field within the loop as shown by the following blue magnetic field lines. In the same way that magnetic field is created within a solenoid. Now, because our electric current is changing, because it's alternating, that means the magnetic field produced will also be an alternating or a changing magnetic field, and that implies that a changing magnetic flux will exist inside the loops of coil. Now, by Faraday's law, a changing magnetic flux will induce an EMF inside our coils of wire. And by Lenz's law, that induced EMF will tend to oppose, will point in a direction that will essentially oppose the change in magnetic flux. So we'll see exactly what that means in just a moment. First, let's review what we just said. When an alternating electric current travels through the loops of coil, it produces a changing magnetic field. Now, because that magnetic field is changing, that will change our magnetic flux. Now, by Faraday's law, a changing magnetic flux will induce an EMF within a coil of wire. So that will induce an EMF within this coil of wire, and that induced EMF will in turn induce an electric current within that loop of wire. Now, by Lenz's law, this induced EMF will create an electric current called the induced electric current that will point in the direction that will oppose the change in magnetic flux. So let's suppose that our electric current that is traveling through these loops of wire, that is an alternating current, is increasing at some given moment in time. Now, if the current that is traveling given by I is increasing, that basically means that the induced EMF will create an induced current that will point in the opposite direction of this electric current, and that's because our change in magnetic flux, our magnetic flux is increasing, and so the induced electric current has to produce an induced magnetic field that points in the opposite direction of the magnetic field created by this electric current that comes from Lenz's law. Now, on the other hand, if the electric current moving in the loop of wire is decreasing at some given moment in time, that basically means our magnetic flux will decrease, and so our induced EMF will create an induced electric current that will create a magnetic field that will point in the same direction as this magnetic field, and that implies that the two electric currents will point in the same exact direction. So once again, if the current in the loop is decreasing at some given moment in time, then the induced EMF will create an induced electric current that points in the same direction as the initial alternating electric current. So this concept is known as self-inductance or simply inductance. Now let's actually define self-inductance mathematically. So in the same way that we were able to define mutual inductance, we can also define self-inductance. Self-inductance is given by uppercase L. So our self-inductance, or simply inductance, is equal to the product of the number of loops of wire found in this particular coil. Let's say that's given by N, multiplied by the magnetic flux within these loops of wire, given by phi M, divided by I, the electric current that is traveling through these wires, given by I. Now, this is known as our inductance. And inductance has the units given by henries, which is given by uppercase H. Now, if we take this equation, we can rearrange it and solve for our magnetic flux that exists within these loops of wire of our coil. So we see if we bring the I and N to the left side, we get the following result. The magnetic flux within our coil of wire is equal to the product of our inductance, L, multiplied by I, our current, divided by N. So, now let's combine this equation with Faraday's law of electromagnetic induction. By Faraday's law, we know that our induced EMF within our coil is equal to the negative of the product of the number of loops given by N multiplied by the derivative of our magnetic flux with respect to time. So the rate of change of our magnetic flux with respect to time. Now, from this equation, we know that this quantity is equal to Li divided by N. So if we take that and plug it in, we get the following result. So we can take out our constants. L and N are both constants. We can take those out, and the I is the quantity that varies over time. So that becomes the following. So our induced EMF is equal to negative of the product and L divided by N multiplied by the derivative of our I with respect to T. So di dt. Notice the N's appear on top and bottom. We can cancel these out and our equation becomes as follows. So, this equation essentially gives us a relationship between our induced EMF and the rate of change of our electric current. So we see if our rate of change increases, that will increase our EMF produced by that rate of change increase. So our EMF is equal to negative of our inductance L multiplied by di dt. So L is essentially a constant, but L depends on the type of coil that we are using. It depends on things like the shape, size, and the distance between our coils. So inductance are found inside circuits. So coils of wire can be placed into circuits, and these are known as inductors. And this particular inductor has an inductance given by L, given by this equation. Now, what exactly is the purpose of an inductor? When we take an inductor, which is essentially a coil of wire, and place it inside an electric circuit with some source of voltage, what purpose does that serve? So let's suppose we have the following electric circuit. So we have some type of voltage source, and that creates an alternating electric current which travels through our electric circuit. So what is the purpose of our inductor? Now, an inductor with a negligible resistance is used to essentially control the changing electric current. So let's suppose we have some sort of source of voltage, and that voltage is given by the following quantity. Now we know from this equation that our induced EMF is equal to negative L multiplied by di divided by dt, where this is simply the rate of change of our electric current with respect to time. Now, for some given quantity of our voltage produced by our voltage source, we see that as L increases, the change in current will decrease. In other words, if this quantity stays constant and we increase the amount of L, this quantity must decrease to compensate this increase so that this constant remains the same. So if we increase the quantity of inductance within our inductor, that will essentially decrease the rate of change of our electric current, and so our alternating current will thereby decrease. So therefore, a large L value will limit the alternating current to a very small value. Likewise, if the L decreases, this rate of change increases and our alternating electric current will also increase. So essentially, the purpose of placing an inductor inside an electric circuit is to essentially limit the rate of change of our current. It is to limit the alternating electric current. So we see that inductance essentially serves to impede the flow of alternating current.